Okay, so this is the second video in the related rates section. In the last video, we mostly talked about these so-called implicit derivatives, and if you're following along on the handout sheet, it was we did basically this much, what you see here, which was to think about and compute and come up with as best we can an attempt at writing down at least something about the derivative of these expressions, I guess, or these things down here. And again, as I think I said in the last video, that's mainly just because we'll be dealing with trying to compute derivatives of things like that, throughout the related rates section. So, which we're now going to actually begin today. So if you scroll or move down on the sheet there, the next thing you see is kind of just a big chart, I guess, or a big strategy guide. So I've put this on slides, so I'm going to go over to that in a second. And then what's next on the next 3 pages are just are just examples. So I'll go through these as well, and I'll flash back and forth between the two just to get the right lingo and stuff down. I didn't put those on slides. So, but let me go back over here and let's go through at least the strategy we're going to use to do these related rates problems. So what are these problems going to involve? Well, so related rates problems are, again, as I think maybe I said in the intro, they're really just fancy. It's just a fancy word for word problems. But what is sort of, I guess, unique about them is that these are going to be problems where we're going to see not just one unknown quantity, but probably several, and meaning at least 2, but sometimes 3. I don't think 4 ever happens in these examples, but you could, in theory, have as many as you wanted. And what do I mean by unknown quantities? So, anything, any quantity that's in a physical problem that you want to know about or that's being discussed, that's some unknown quantity. And by unknown, I mean, well, as the word would suggest, you don't know exactly what it is, right? So, for example, if in a problem you have an object that weighs 5 pounds, that's not an unknown quantity. That's a known quantity, right? It's 5 pounds. So that's not what I'm really talking about. What I would be talking about more is that I take that 5-pound object and now I throw it through the air. And I want to maybe model or talk about the height of the object, the speed of the object, things like that. Oh, okay. Those are quantities that are changing in the problem. Okay, so, and they're unknown to me in so much as I don't actually know. I mean, unless I'm a weird, crazy person, I probably don't exactly know what the height of the object or what the speed of the object is at any given time. I probably don't just know that off the top of my head, right? So, so what do I mean by, or in these related rates problems? There's going to be several unknown quantities, and the quantities, so again, some of them will be, some quantities in the problem will be fixed, and we'll know them. But many, or the stars of the show will be the quantities that are unknown to us but are changing. So, and again, that's basically that's the main idea of what modeling is all about, is that you have some quantity that's changing and you don't know what it is, and you want to study it and try to figure out what it is, or make predictions about what it might be 10 years from now or whatever. So all right, now if that was the end of the sentence, right, then I wouldn't call these related rates problems. I would call them rates problems, I guess, right? I would sort of cross out that word. But this would also be the world's shortest lesson, because I would then now throw my hands up in the air and say we're SOL, because I can't just magically come up with an answer to tell you about the speed of some rock that you threw in the air unless I know some other stuff, and unless I know that there's some relationship between the things I do know and the things I don't know. So the other key piece, why is the other R there, related rates, is that not only are these objects changing, but I should say these objects are changing and I don't know what they are, these quantities, but they are changing in a related way. Okay, now I know words kind of, it's easy to kind of let these words just sort of wash over you and be like, when is he going to just start doing the things that I need to do problems? And I sympathize with that. But I really have to pause and just say, okay, what is that? What is, what is the thing that sort of ties all these problems together is what I just said, this idea that you have these quantities that are involved in this problem and you want to study them. You don't know what they are, but you do know that they are evolving or changing in a related way. And by that I just mean that how one of them changes is related to or dependent on how one of the other objects in the problem changes. Okay, a classic example being, you can't see me right now, but if I was standing in front of you in class, I would hold up my arm and say, okay, what are different types of ways that I can change my arm? Well, let's say I want to study where my hand is. Well, I could study the motion of my elbow, right? I could bend it and move it up and down and flex it and stuff like that. Now, am I changing my hand itself? No, I'm just moving my elbow. But I know, right, because of, well, physics or just being a human being, right, that moving my elbow is related to or has an effect on how my hand moves, right? Or maybe should say it the other way. The motion of my hand is related to, and maybe I would even say dependent on, the motion of my elbow. So if I know something about how my elbow is changing, I could probably use that, hopefully, to come up with some way of describing how does my hand move. Okay, similarly, I could say, all right, but wait a minute. It's not just my elbow that influences where the position of my hand. It's also my wrist. I say, okay. So now I've got maybe 3 quantities. I've got my elbow, I've got my wrist, and I've got my hand. I don't know where any of them are. Imagine that I'm pitching a baseball, right, which certainly involves all of those things. I want to make some sort of a statement about how the speed of my hand is, right, which is holding the ball, as I wind up to deliver a pitch. Okay, well, if I know stuff about how my elbow is moving, and maybe I know stuff about how my wrist is moving when I pitch a ball, could I maybe use those things to together come up with an equation or a function for how the ball is going to move? I mean, I know that that's probably hard, and that is hard, right? But at least spiritually, doesn't that make sense that since those quantities interact with each other and change in a related way, that I should be able to sort of, if I was a super smart person and like a supercomputer brain sort of thing, I should be able to sort of take all that in and somehow compute something that would then say, okay, so here's what the ball is going to do. And that's a probably way harder and scaled up version of what it is we're going to do. That's the basic idea, and hopefully that makes sense, that we're going to be looking at trying to study the problems we look at, are going to be looking at, you've got some quantities, they're changing in a related way, in fact, in a dependent way, you might even say. And I want to be able to say, okay, if you tell me about how this one thing is changing, you give me enough information, maybe I could tell you how the other object is changing. Okay? So that's the basic idea or setup here. So that's pretty much what this intro paragraph here says, right, is that this is what it is we're going to be studying. And I'll just say, remember, t is our variable now, time. And remember the other comment I made, which I think probably I made in this chart as well, which is that we should always think of the derivative now as being synonymous with the word rate, or rate of change of some object. So just sort of keep that in mind as we go through these problems. So what is our strategy going to be? I hesitate to give you sort of what is quite obviously a sort of long and involved chart here of steps, because you haven't even seen a problem yet. So, but I'll go through it, at least once here, so that you have some notion of how we're going to proceed. But flip back to this chart. Again, if you've printed it out, that's probably a good idea. Not just periodically, but consistently, as we go through our problems to try to say, okay, what step are we doing right now? Why are we doing this? And then, of course, as you go to do your problems in homework and on quizzes, exams, etc., think about this chart and think about trying to follow it. It's not going to make a whole lot of sense right now, but bear with me here, right? Again, try to maybe think of the example I already gave you of, pitching a baseball, and the quantities or the unknown quantities involved in that, and the relationships between your elbow and wrist and the ball moving, okay, and all that stuff. So, all right, so step one probably, which is true of almost any word problem, is draw a picture. And we're going to probably do that in all these problems for the most part. And when I go to label my picture, one thing that's going to save you some anguish later is when you draw the picture, okay, you've got this set up. There's going to be some quantities in the problem that are changing and other quantities that are fixed. In other words, don't change. Quantities that are fixed, that are always whatever they are, put whatever they are in your picture. In other words, if you have an object in your picture that's 20 feet long, and it's always 20 feet long, then when you label that in your picture, put a 20 on it. Don't get crazy and put other stuff like, oh, it's a random, okay, no, it's 20. It's always 20, so just put 20 down. Okay, now, but as promised, right, some quantities in our problem are going to be changing. All right, so what does it mean to say that a quantity is changing? Well, you know what that means in English. But for us, in terms of labeling, what should I do about that? So in other words, you have some object that maybe starts at 5 feet, but it grows over the course of the problem. It's getting longer. Well, I can't just say it's 5 then, right? Because that would sort of be wrong. It's not 5 all the time. It's changing. So what I want to do with any quantity in my problem that's changing, is all I really want to do for labeling purposes is label it with a function, not a number. Now it's going to be tempting because we're going to ask a question like, what's happening when that object is 10 feet long? So it's going to be tempting to say, oh, so it's 10? But no. If it started at 5 and it's growing, it's not always 5 and it's not always 10. But the point is that it doesn't really matter what it is, right, at any given time for us right now. What we do want to do, though, is denote in our picture, this is a quantity that changes. I'm going to label it with a function. And what does that mean? That means label it with something like A of t or B of t, or if it's an object that, maybe it's a kite, like the string of a kite. So maybe you'll call that K of t for the kite, whatever you want. You make up whatever letters you want to use here, right? Or F, you could use F, that's fine, whatever you've got. Label them with functions though, right? So, and again, right, what does it mean when I say A of t or B of t? It means that's some quantity that depends on time, right? It's a function of time. It's going to change over time, okay? So go ahead and do that. That's step one. So draw a picture, label it. Things that don't change, label them with what they actually are. Things that do change, label them with functions that make sense to you, and pick letters that make sense. I put this sort of second blurb in here. Most of the time you can't do that, so I'm going to kind of just actually skip over that. But, well, in the event that you can, maybe come up with an expression for that. But for the most part, that's impossible, so I'm going to just go ahead and skip that. All right, so step one, draw a picture. Step two, well, I promised you, right, in my little intro, that we weren't just doing these problems, in an arbitrary world. The quantities in my picture, right, or in the problem, are changing in a related way. In other words, there is something that's tying the quantities in our picture together, with each other. So that is of super importance in this problem because, again, I'll keep going back to my baseball example. If I said, predict for me the motion of this baseball, if I tell you about the motion of a car driving down the street and the motion of a tree in China swinging in the breeze, you would be like, I don't see how those two things that you're telling me about in any way influence me throwing a baseball. And you'd be absolutely right. Because there would be, in that case, we would say, there's no relationship tying together the speed of a pitch that you're about to throw and whatever those two silly things I just made up, a tree swaying in China, and I don't remember what else the other thing I said was, right? So those would be completely unrelated. But in our problems, these quantities will be super related to each other, and they're going to be related together by an overarching connection or fact that ties them together. Again, this will make more sense when we look at problems more specifically. But of crucial importance is that you identify what is that overarching fact. Now here's where I know you all have understandably a desire to try to be like, okay, so I always just do this and then I get the right answer? And that's impossible for word problems. But this is the best thing I can do for you, is I can say you generally have three types of overarching facts. One, if you have a triangle, a right triangle in your problem, one fact that you know that ties together the three sides of a triangle is the Pythagorean theorem. So that's going to be a go-to type of a problem, where if you have a triangle and the sides of the triangle are changing, one thing you can say always to tie those changing quantities together is that the Pythagorean theorem always must be observed, or in other words, it always must be true. So one way of relating the sides of a triangle is just by using that overarching connector. And I'll just, again, we're going to do lots of examples, right? But hopefully you can kind of get an appreciation then. If I tell you about how A and B are changing, which are two sides of a triangle, doesn't it kind of make sense that you should be able to maybe figure out how the third side is changing, right? If I imagine you sort of have a magic triangle and you start bending and flexing and stretching and shrinking two of the three sides of a triangle, doesn't it just sort of drag the third side along for the ride in a sort of predictable way? So that's basically all this is saying, is that you do have a way of connecting the three sides of a triangle, and in fact, through thousands of years of math, you have an actual equation that says that's how the sides of a triangle are related to each other. So we might want to use that. Okay. The other thing, if you have a triangle, which we're going to have a lot of in these problems, it will be right triangles. The other thing that you could use to tie together quantities in a triangle are trig identities. And this is maybe the first time in your life that you've been probably forced to learn trig stuff against your will in algebra and pre-calc and trig and all, and even in our class. And you've probably always been like, when the hell am I ever going to use this for a problem that isn't just manufactured? Well, finally, here the answer is here. Because what do trig functions do for us? Remember, in our introduction, and whenever you learn trig in the first place, trig functions serve to be a connection between the angles in a triangle and the sides, or the ratio or fraction, right, of the sides of the triangle. That's what the trig functions do. So, for example, sine of whatever is the opposite side divided by the hypotenuse side, and the others that are in our chart, right? So a trig function is a wonderful connector because it does exactly what we're trying to do here, which is to say, what is the dependence? What is the relationship between my quantities? Well, if you want to talk about angles of a triangle and what effect that has on the sides of the triangle, trig is your friend. As much as you thought you'd never say that, trig is then going to probably be the overarching fact that connects the quantities in your problem. And again, this will make sense when we do these. But the key observation here is going to be, if the question asks you about angles or tells you about angles, you have to use trig, period, end of story. Okay, so that's one thing I can say for definite, is that if you have angles and it says, this is growing at a rate of, 0.1 radians per minute or something like that, or whatever, you need trig. Because if you're trying to establish a connection between an angle and some sides of a triangle, right, lengths of things, the trig is the only possible way to do that. Okay? And the third, generally the third kind of related rates problem is one that involves an area or volume. So it's some physical system that's changing, and you want to make some connection between how some quantity changes and maybe the whole thing. So for example, you have a sphere, right, a ball, and maybe the radius of the sphere is growing at a certain rate. It's expanding, right? Well, that makes the volume of the sphere bigger, right? I don't have to tell you more specifically than that, but you could probably come up with a more specific relationship that says, oh, if this radius grows at blah, blah, blah rate, then probably the volume of the sphere is growing at blah, blah, blah rate. Okay, so, and how would I ever get my hands on the relationship between the radius of a sphere and the volume of the sphere? Oh, there's a volume formula that tells you that the volume of a sphere is, I think it's 4/3 pi r cubed. Okay. So if you've got those types of questions, probably the area or volume formula is going to be the connector that you want between the unknown quantities in your problem. Okay, I wouldn't say, like I said, don't hold me to this. This is not an exhaustive list. You may have some other sorts of connectors that are floating around, but mostly it's one of these three types. So, okay, so step 2 is to write down your fact. Your overarching fact is what we'll usually call this thing, or your master equation, or whatever you want to call it. It is the thing that once you draw your picture is going to tie the pieces of your picture together in an equation. Okay? All right. After you do this, what else do you still have to do? Well, you haven't really done anything. This is all just sort of set up at this point. So now now will come the actual questions. So now in some of these problems, I will just ask you to basically, there's one sort of main question, and maybe that's all I'll ask you, in which case you have to do a bunch of steps before you can probably answer the main question. In other cases, I may ask you lead-up questions, as I say here, like parts A, B, C, D of a problem might be lead-up questions that are leading you towards the answer. Okay, but in either case, the main question in these questions is going to often involve you wanting to know about how does blah, blah, blah change at some specific moment in time. That's pretty much what all these questions the main question at least in these problems will involve. So if I want to know at what rate, let's go back to my original example of throwing a baseball, I want to know what speed will the baseball have when it leaves my hand when I pitch it, or when it hits, the home plate, or arrives at the batter. That's a rate, right? Speed, that's a rate, miles per hour, or whatever it might be. So I would need to know, for example, what's the derivative of the position of the ball? That would be the speed. So in all of these problems, the main question is going to be, tell me at what rate does blah, blah, blah change at some specific moment. So in order to get there, right, in order to even be able to talk about the rate, I need to introduce a derivative, because that's what derivative is the rate, right? These overarching facts that I have up here they're not derivatives, right? They're just facts. They're, a squared plus b squared equals c squared, or sine of x equals, a over b, okay, or whatever letters you're using for your quantities, right? They're just statements. They're not derivatives. So how would I ever introduce a derivative? Well, this is exactly where this implicit business is going to come into play, because what is my main calculus step is right here. When I write down my overarching fact, I may have some lead-up questions that I'll answer first. But at some point, in order to answer the big question, I'm going to have to take the derivative of your, what did I call it, master equation? Okay, overarching fact, same thing. Take the derivative of that whole thing. Well, we're going to see this in action, right? But there's going to be a bunch of pieces in your overarching fact. Let's just use Pythagorean theorem because it's right there. Well, a squared plus b squared equals c squared. Okay. Well, those a, b, and c might all be changing. Those might be sides of a triangle that are changing. So those might all be really a of t, b of t, c of t. So if you want to take the derivative, you've got to take the derivative of each one of them. And each one of them is going to be an implicit derivative, like we did in the last video. Okay, what about trig? Trig is the same thing. If I have trig, sine of something equals a of t over b of t. Well, if I want to take the derivative, I'm going to need an implicit derivative, just like we did, again, in the last video. So you'll see these in action. But that's going to be the crucial step, and that's really the only calculus step involved in these problems. And it's mainly just using the implicit stuff that was in the last video. Okay, so we're going to take the derivative of the whole thing, which is going to generally produce a bit of a mess. But the good news is that then after that, it's not hard. So once I take the derivative, hopefully correctly, my last step is to now say, okay, I've taken the derivative of this fact, which you can do, right? Taking the derivative, right, as a process is just like saying if I add 1 to both sides of an equation, you know that that's legal. Well, taking the derivative of both sides of an equation is also legal, right? Because it's basically saying an equation says the stuff on the left is equal to the stuff on the right. So the rate at which the stuff on the left changes better be equal to the rate at which the stuff on the right side of an equation changes, right? Otherwise, how could they always be equal? So it's legal to take a derivative of an equation as long as you do it to both sides. And that's where, again, these implicit derivatives are going to pop up all over the place. All right? So once you do that, what are you going to be left with? A whole mess of stuff. And there'll still be an equal sign in there. But what is it then that probably is the last step, or basically the last step of these problems, is that you're going to want to know specifically, the question part of the question is going to say, specifically, tell me about one of these quantities, how it's changing at a specific moment in time, or a moment in the question. So after you take the derivative of this big nasty equation, now you can say, okay, that's always true. That derivative in this awful equation I'm looking at, that's true at any time. Now let me zero in on the moment that the question is actually asking about. Okay, so the question wants to know what's happening at time 5. I just made that up, right? But let's say they want to know what's happening after 5 minutes. So after I do all this work, I can now say, okay, let me now plug in everything I know about time 5. The lengths of things, the speeds of things, the angles of things, whatever I've got in my problem. Now let me say, okay, I'm going to now advance to the specific moment in question, and I'm going to plug in everything I know about that moment. And I promise you, if you do it correctly at least, you'll know everything in your big nasty equation except the one thing that you were trying to solve for. So once you get to the last step, it's just arithmetic to plug in all this stuff, you know, use your calculator and do some computing, and then there's going to be one thing you don't know, and that's going to be the thing that you are being asked about, hopefully. So solve for that, and that's your answer. All right? And again, this is just sort of a, I've probably already said this several times, but I'm going to say it many, many more. This is the also, people mess this up, and you're I'm sad to report that some of you will do this wrong, even though I'm warning you not to do it wrong. You're still going to do it wrong. So try not to be that person. Remember, if a question is asking you how big or how long or how whatever, the value of something, that's talking about the master equation, the whatever one of these three you're in. If something is, and those are talking about things like A of t or B of t or whatever you've got. But questions asking you about how something is changing are referring to derivatives. So things like A prime or B prime. Okay, so any information that's talking about rates or asking you about rates are referring to the derivatives of these quantities that are probably in your master equation. So please please try to just be careful that you don't confuse them and say, oh, this says that this side is changing at 5 miles an hour. So 5 is how long the side is. No, it's not. It's how the side is changing. It's the derivative of that side, not the length of that side. Okay, again, sorry to be negative. We haven't even done a problem yet, and I'm already pointing out the future mistakes. But this is just, again, somewhere that I know a lot of people get fouled up. So, and again, only plug in, I should also underline this last sentence because this is also a point of confusion for folks. You can only really solve and finish a problem and start plugging in stuff about the specific moment in question after you've taken the derivative. So the last step is always plug a bunch of stuff in. Don't do that prematurely, otherwise you're going to advance to that moment before you meant to. So, and again, I'll point that out to you in problems. So, all right, so that's the lesson part of this, I guess. That's the best I can do to try to sort of give you a strategy guide or steps for how to do these problems. I mean, I could go on and on and on and give you, 5 other versions of those steps, and it's not going to be all that helpful without actually trying some problems. So I'm going to do several of them with you here. You really need to do these problems. Again, I can say very few things for sure, but I can say with pretty much 100% certainty, if the first time you're really trying these problems, and by trying them I mean without my help and without guiding you through them, if the first time you're doing that is on a quiz, you're going to fail the quiz. If the first time you're doing that is on the exam, I guarantee you will fail the exam badly. You really need to try these. They are hard. You're going to struggle with them. You're not going to get them the first time. So you're going to look at this, you're going to look at solutions for the homework problems, and really try to understand the steps and say, okay, that's what we did there. Okay, I see that now. And come back to these videos, because I'm going to be very slow in going through these problems so that you really understand why we're doing what we're doing. And that light bulb has to go off, though, at some point for you. And if it doesn't, it's going to be a rough exam, I guess is all I'll say. And this is the hardest material, I think, of the whole course. I think most students who have taken calc would say this is the hardest stuff. So really try to commit yourself to thinking really hard as we go through these examples to really understand what are we doing, why are we doing it, et cetera, et cetera. So, okay, I think I maybe have time in this video to do maybe the first problem that's on the sheet here. So let me grab that. Okay, so the question says that you're standing 100 feet south of the train station here, and a train pulls out of the station going east, which probably doesn't make a whole lot of sense to go east from here. Well, okay, it's going up to Rockport or something maybe. So it's going east at 15 feet per second. Okay. So this is an example of a problem where, since it's the first one we're doing together, I'm going to kind of lead you through it with these parts. In the future, I would probably mainly just ask you the last part of the question, which is part E. At what rate is the distance between you and the train changing when it's 125 feet away from you? But I'm pretty sure if I asked you that question right now, you would, rightfully so, throw up your hands in the air and say, I have absolutely no idea how to do that. And that's fair at this point. So let's not jump right to part E, and let's do parts A, B, C, D first. Okay, so it's a pretty simple setup, right? Train, you're standing, right? So I'm in this problem, and I'm 100 feet south of the depot, and a train is leaving the depot going east at 15 feet per second. Okay, so that should generate some sort of a mental image. So let me just go slow here and say, all right, let me do step one of my process, which is to draw a picture, and I'm going to label both the fixed quantities, things that don't change, and the things that do change. And those I'm going to label, the things that do change, I'm going to label with functions. The things that don't change, I'm going to label with numbers. So, things that don't change, say how much it is and be done with it. Okay. So let me go over to the slide so I can write this in. Okay, you're 100 feet south and it's going 15. Okay. All right, so step one, draw a picture. All right, so well, let's see. We're part of this problem, so let's put us down. Okay, and we're the depot. We're 100 feet south of the depot, so let's call that. I'm not going to draw a train station, so I'll just say depot. And the train leaves the depot going east, which of course would be this way, and that's where the train is. You can kind of draw an arrow if you want to indicate that it's moving or not, doesn't matter. Okay, hopefully this isn't too hard yet. I'm pretty much just writing down the description of the problem. But, I mean, I don't know. Even if I don't, I'm not sure what else I would do here except to hopefully realize and kind of see, I hope everybody sees that there's a triangle here, isn't there, right? Between me, the depot, and the train. I'm hoping it's not a leap of faith to say that you would maybe notice, well, how are all the things related in this problem, or what's the connection between me, the depot, and the train? A triangle, I guess, right? I mean, so I'm going to just draw the triangle in here so that it's sort of a complete picture. Okay, so hopefully that's not a leap of faith to say that you would maybe draw the triangle in there. And so, all right, well, what else do I know? So that's kind of the picture. That's the setup anyway, right? So, all right, but I was supposed to label things in my picture, label quantities in my picture. And I'm supposed to label quantities with numbers if they don't change, or with functions if they do change. So I would ask the class right now, I think one of the quantities, one of the sides of my triangle, doesn't change, right? I'm not moving, and the train station isn't moving, which means at the beginning of the problem and at the end of the problem, no matter where I am, that side is always 100. So label it with 100 rather than with a function. But the other two sides of my triangle are most definitely changing over time, because over time means as the train moves, right? The train is the thing that's actually moving in this picture. Well, of course, the distance between the depot and the train, that's going to change. And the distance between me and the train, that's going to also change because the train is moving. So these other two sides of the triangle are indeed changing. So I should label them with functions rather than numbers. Because in particular, I don't even know what those numbers should be. Now you could look ahead in the problem and you're going to see numbers given for the sides. But that's not, A, that doesn't matter right now. And B, those two other sides are not always whatever numbers are later in the problem. They are most definitely changing. Okay, so any side that's changing should be labeled with a function. Now, maybe because I have a little bit of insight, I'm going for probably a Pythagorean theorem here because I've got a triangle staring me in the face. So why don't I label that side A of t? Now this side is 100, which would sort of play the role of B in Pythagorean theorem. And the hypotenuse side, which is the third side here, I think in Pythagorean theorem we usually call that side C. So I'll call it C of t though, right? Because again, it's changing, so it needs to be a function, not just a number. Okay, so that would be what I would draw as my complete picture to this problem, because it describes the objects, which are the train, the depot, and me. It describes the quantities that are part of my problem, which are the three sides of the triangle. And it describes, as best I can, what can I say about each side. This side I can say is 100, so I labeled it with 100. And the other two sides are both changing over the course of the problem, so I've labeled them with functions that I can then reference later. Okay? So hopefully everybody's okay with this and clear on this, that A of t up at the top there represents what? How far the train has gone along the tracks, right? The tracks are sort of, that is actually what A of t is the tracks if you want, right? So A of t is how far has the train moved along the tracks, and C of t is the distance between me and the train. Okay? All right, so let's go back to the question and see. I think that's part A of the question completed, I would say. So what else does it want me to do? So part B says, is basically step 2. Come up with a fact, an overarching fact, a master equation, that ties together the changing quantities in this problem. Okay? All right. So I'm looking for a fact that ties together the quantities in my problem. Well, the quantities in my problem are the sides of the triangle. And so again, right, I've given you a little bit of a hint or intuition that Pythagorean theorem is a good thing. It's a connecting fact. It's always true. And so that's pretty good for us in this problem. So I'm going to use, as my master equation or my overarching fact, I'm going to use the Pythagorean theorem. So my, sort of master equation or my overarching fact that I know that ties together the quantities in my problem would be that the Pythagorean theorem, which says that the A side squared plus the B side, now B is 100, so I'm going to literally just fill in 100, squared, has to be the hypotenuse side squared. Okay, so that's true at any time t, right? If I told you that the train had traveled 200 feet from the depot, then I could plug 200 in for A of t, and I would say 200 squared plus 100 squared equals c squared. And then I could solve for c. Okay? Or if I told you the train is 1,000 feet away from me, I could plug 1,000 in for c of t, and then I could solve, and I could say, oh, okay, I could solve for A of t then, right? So this is a fact. It's a fact that's always true, but it's a little bit of an arbitrary fact because I don't know what A of t is, and I don't know what C of t is. I know what they represent, but I don't specifically know how long either one of them is. But that's okay, because this is an overarching fact which is true at any time t. Okay, so I really should have probably printed this out. um, so the next part says, so that's part B. Part B is done. All right, so part C says, how about, can you do a little bit of predicting for me? So how about in 3 seconds, 3 seconds from now, could you tell me how far, where is everything, basically, right? Or in other words, let 3 seconds of time go by and tell me about how far away the train is from you, and probably just tell me facts about where everybody is after 3 seconds. Well, and remember, we do know this fact, right? That the train is moving at a rate of 15 feet per second. Okay, so let's not forget that we know that one. All right. So, so it wants to know what's happening after 3 seconds. All right, so, well, one thing I actually know, right, is that the train is moving, and maybe you could put this in your picture if you want. I'll just put it here so I don't forget it. The train is moving at a rate of 15 feet per second. Now, if I was to ask you, what does 15 represent? 15 is not A of t, right? A of t is how long, or what's the length of that side. In other words, how far has the train traveled? That's A of t, which is not 15. But I would hope you would be able to maybe recognize that 15 is actually the derivative of A. Because why? 15 feet per second represents the rate at which that side changes. It's growing by 15 feet every second. That's true, it is, right? Because that's the train. That's the, movement of the train. So 15 is not A of t. 15 is actually A prime of t, or it's the derivative of 15. Of A. So this question wants to know what's happening after 3 seconds. Well, that's actually not too hard to be able to figure out, right? Because could you tell me how long the A side is after 3 seconds? So I'm sorry, what part are we on? We're on part C. So part C is saying, tell me what's happening at time 3, right? So my master equation over here works at any time. So in particular, at time 3, it also is a valid statement. But what would this say at time 3? It would basically say, how long is the A side at time 3 squared plus 10,000, which is 100 squared, equals how long is the C side after at time 3. That's what that would say. So at time 3, in order to figure these things out, all I really need to know is how long is the A side, because I can then use Pythagorean theorem to figure out how long the C side is. Well, I think I know how long the A side is after time 3. This is where you have to just use a little bit of intuition here, right? So how long is the top side after 3 seconds? Well, remember, the train is moving at 15 feet per second. So hopefully this isn't a huge leap of faith, right? It's traveled 45 feet after 3 seconds, right? Because it's 15 feet per second for 3 seconds. So actually, at time 3, A of 3 is 45. Oh, but I always know, right? My master equation is always true. If you give me the length of A squared plus 1,000 squared, that will equal the length of C squared. So using Pythagorean theorem, or using my master equation, I know that 45 squared plus 100 squared equals C squared at this specific moment in time, right? At time 3, I know that if I can tell you how long A is, which hopefully I convinced you is 45, that if I plop that in and use the Pythagorean theorem, that should be enough to, to be able to solve for, in this case, C squared. So if I do 45 squared and I add 10,000, you get 12,025, and that's C squared, or C of t squared. So if I take the square root of that, I'll just round this. You get about 110. It's almost 110, but 109.7 feet. Okay, so all that's saying is that after 3 seconds, and in fact, it's not a terrible idea to draw yourself like a mini version of the big picture. At time 3, that side's 100, because it's always 100. This side is 45, and this side would then be this 109.7. Okay? So this didn't use any calculus, right? This is just algebra, or at worst, pre-calc. Okay, now that's not probably the main question, because in particular there's two more after it, but also it doesn't really do anything with the rates, a little bit, but not a whole lot yet, right? So I have more to do still, I think, right? Okay, so the next question says, all right, well, could you tell me when the train would be 125 feet away from you? Because apparently time equals 3, right? At time equals 3, the train is only about 110 feet away from you. That's what we got in the last part. So I say, well, that's not the moment I really cared about. Maybe I care for, I don't know for what reason, but for some reason I care about when the train is 125 feet away from you. Could you tell me when that is? Okay. So this is still yet just another sort of lead-up question. So what is that saying? That's saying I'd like to know when the C side, the hypotenuse side, when is that 125? That's what it's asking, right? So part D here is asking when is C, the C side, equal to 125? Well, I don't obviously know that offhand, but I do have the Pythagorean theorem, or I do have my master equation, which again, I can't say this enough, you probably mostly just keep going back to the same fact, which you do. That says, all right, I always know that the A side squared equals 10,000. The A side squared plus 10,000 is the C side squared. So, all right, if you want to know when C is 125, let's just ask, let's solve. That would be saying, well, the A side squared plus 100 squared, when is that 125 squared, right? Because that's, to say C is 125 means this fact would have to work at some point. So could I use this to then solve for A? I think so, right? So if I do the same, if I just do some arithmetic here, right? I do 100 squared, which is 10,000, and I subtract that from 125 squared, and I take the square root, you're going to get that A is 75. Okay, so now that's not, I guess that's not quite the answer, but I think what this is saying is that if you want this side to be 125, remember this side's always 100, well that must mean that this side is 75 is what that's saying, because right, that's saying, that's what we just solved for. We said, how long is the A side when we know the other two sides? Well, okay, it's 75. Now when does that happen? I guess that should be a time, shouldn't it? But remember, you know the train is going at 15 feet per second. So how long does it take to travel 75 feet? Hopefully, again, this isn't a leap of faith. If you divide 75 by 15, you get 5. Okay? So this side is 75 feet long when time is 5 seconds. Is that what I'm using, feet per second? Yeah, seconds. Okay? Again, because we know the train is going 15 feet per second, right? So how long would it take for it to travel 75 feet? Oh, 5 seconds. Okay? So, all right. Now, I will repeat again, I haven't really used calculus yet or any of this sort of stuff we've been working on, so it must be that this last part is where I'm going to use it, and indeed it is. So the last part says, which I think I remember, it says, at what rate is the train, what rate is the distance between you and the train changing when it's 125 feet away from you? So part E, which I'm going to now do right here under this, is asking you at what rate or what speed is the distance between you and the train changing when it's 125 feet away from you? Okay. I should just make sure that that's what this says. Right? Okay, yeah. At what rate is this between you and the train changing when it's 125 feet away from you? All right. So that's the question. Okay, that's the real one that we need some help with. So how would you know that, or how do you know that that's not as easy as the couple ones we've just done? Well, for starters, it asks you about the rate at which things are changing. And in particular, what is this question asking? So I think it's important when you get to these problems to ask yourself, what is it that I'm trying to actually figure out here? It'll help you, I think, not be, sort of confused with, when do I do what? Oh, let me memorize all the problems we do. What is it that I always do in this? No, you can't do that. You have to understand, why are we doing this now, so that you'll know in the future, oh, okay, now I understand when we do that. So I get to this problem. It says, tell me the rate at which the distance between me and the train is changing when, or at the moment, that the train is 125 feet away from me. Okay. So there's a lot to understand in that question. But first of all, let me just ask the question, what is the quantity that I'm looking for? I guess is a good question, right? Well, it's asking me for, it's talking about the distance between me and the train, which is c. But it's asking me about the rate at which the distance between me and the train is changing. So the question is asking me, we're trying to find the rate at which the distance between me and the train, the distance between me and the train is c, and the rate at which the distance between me and the train is changing, that's c prime. So what is it that I'm actually trying to find? I think it's helpful to write this down before you launch into this. I'm trying to find c prime, but now at what moment am I talking about? Well, it says find the rate at which the distance between me and the train is changing when the train is 125 feet away from me. Oh, wait a minute, that sounds familiar. In part D, that was exactly what I computed in part D, wasn't it? I figured out that time 5 is the moment when the train is 125 feet away from me. So what I'm really asking in this problem is, tell me that. Compute c prime at time 5. Okay, again, I would pause here for a minute and just try to let that sink in. Do you know how to identify that in the future problems? The answer is hopefully, and if the answer is no, it hopefully will be, okay? So that is the thing I'm looking for. Now, it's important to acknowledge that because, number one, it'll help you sort of, when you get that, you'll be like, oh, good, I'm done with the problem. But also, this is how you know you're supposed to take a derivative right now, because this question is asking you about the derivative of c. Well, my master equation, which is right here, has a very lovely c of t in it. It's right there. But that's not c prime. That's not the derivative of c. That's just c itself. So how do I know that I'm supposed to take a derivative right now? Because it's asking me about the derivative of c. And the only way I'm going to introduce that is to compute the derivative now. Okay, again, this is where you have to do a few of these, but it's not a random reason why we just randomly decide to compute the derivative at some point. No, we're computing the derivative because it's asking us to do that. Okay? So I need to compute the derivative. Now, I can't do this like we've done all semester, where it's, okay, what's the derivative of cosine of t? Because that's not what I'm looking at. The only thing I can compute the derivative of is this big master equation. And that is what I'm going to do. So I'm looking for that. So in order to do that, I'm going to compute, sorry, this is a little bit messy, I'm going to compute the derivative of this entire equation, of my master equation. Okay? Now, let me erase this. Sorry, I should have just erased that. Okay, you all have that written down, so. All right, but what I'm going to do now, right, is I'm going to compute this derivative. So let me just do this like I usually do. Derivative. Now, in order to compute the derivative of this whole equation right here, okay, I need to know what's the derivative of each piece. Do I know what the derivative of a of t squared is? Well, flashback many, many slides. This is what we did these implicit derivatives for. This is exactly when I need the implicit derivatives to say, oh, I have a function squared. Do I know the derivative of that? Yes. Look back in your notes and you'll see we computed this, that the derivative is that. 2 times a of t times a prime of t. So I'm not going to say anything more about that because we already went through how to do that. So, okay, that's the derivative of the first piece. Great. This number here is 10,000, right? 100 squared is 10,000. What's the derivative of 10,000? What's the derivative of any constant number? 0. Wonderful. Okay. Equals, don't forget the equal sign comes down because I'm doing the derivative of both sides of this equation, so they're still going to be equal. And now I want to know what's the derivative of c of t squared. Well, hopefully it's not a leap of faith, right? The derivative of a of t was 2a times a prime. So the derivative of c squared, well, by the same logic, should just be 2c c prime. Okay? So again, it's an implicit derivative. Go off to the side if you want to do it out, and you should. You should do it out, but since we've already done it, I'm going to move past it. So my master equation, I've taken the derivative of it, and I've derived basically what? Like a new equation, I guess, right? Or a new equation that involves now these things. Okay, it's still an equation because I still have an equal sign there. So, all right, fine. So this is true at any time t. Now again, why is this good? Remember, I'm looking for c prime of 5. Remember that, right? Well, oh, look at that. I have a c prime in my problem. Well, that's progress, right? Because I didn't have that. So I can definitely compute, or at least I have that in my problem. I have hope now that I could maybe actually solve for that. And that's exactly what I want to do right now. So this is the last step of my problem is I can say, now let me plug in everything I know. Plug in details or facts about the moment in question, which is time 5. Remember, that was my whole point down here was I want to know what's happening when time is 5. Okay. Well, let me plug in time 5. Okay, well, what do I get? I'd get 2a of 5 times a prime of 5. That's 0, so I don't need to write that down. And then 2c of 5, c prime of 5. Okay, the whole point is that after I've taken the derivative, that's true at any time t. So in particular, it's true at the time that I care about, which for some reason is time 5. Okay. Now, my hope is that I know what most of these things are, and I'm kind of in trouble if I don't. But I think I do. So let's take a look. So what do I get? I'm going to try to squeeze this in here. So I get 2. What's a of 5? A of 5, a is the top side. And at time 5, how far has the train moved? Well, remember, down here in this picture, in part D, I actually drew a picture of what the situation is at time 5, didn't I? I said at time 5, this side is 75, and this side is 125, and that side's 100. So I know what a of 5 is. It's 75. And in fact, I know what c of 5 is. It's 125. Now, I don't know what c prime of 5 is, but that's okay, because that's what I'm looking for. So I better know what a prime of 5 is, otherwise I'm kind of in trouble, right? Well, a prime is the rate at which the a side changes. Oh, wait a minute. I know what that is. It's 15. Now, the fact that it's at time 5 versus time 10 or time 20 doesn't make a difference, right? Because the train is moving at a constant speed. So it's always 15. The rate at which that side is changing is always 15. Okay? Well, I think I'm actually in very good shape now, right? Because everything I see in front of me now is just a number, except for c prime of 5, but that's what I was looking for. So I think all I have left now is just some basic arithmetic to be able to get my answer. So if I do 2 times 75 times 15, I get 2250. And if I do 2 times 125, I get 250 times c prime of 5. So if I divide by 250, you get 9. And it's a rate, so I should put I guess I should put the right units there. It's feet per second, because it's speed, right, or velocity, if you want to say that, right? So c prime of 5 is 9, which means that the distance between me and the train, which is the hypotenuse side, is growing at a rate of 9 feet per second at this moment in time. Okay, so I think I'm almost at the hour mark, so I should probably stop this video. So stay tuned because I'll do some more, the rest of the examples on the sheet.